In this video, we're going to look at reaction coordinates and look at some energy diagrams to get more familiar with some concepts about activation energy and transition states. Okay, so we have this reaction here. So we have initially on the left here, we have our reactants. And then they go up in energy, up the activation barrier, up to the transition state. And then once reaching the transition state, they go down in energy, down to our products. So as drawn here, this would be, if this was the Gibbs energy, this would be an exergonic reaction. It would be spontaneous because we had a decrease in Gibbs energy during this reaction. So some quantities that we want to label in there is that we have going up there from the reactants to the transition state. Let's say that this is some reaction where we have, I don't know, let's just call this R. Let's call this P. So this is a reaction of R going back and forth to P. So the reaction would be reversible. You could go in the reverse direction. So this arrow that I've got here, that would be called the energy of activation, and of activation is often used with a kind of double dagger symbol there. So that would be our delta E of activation, how much energy it took to go from the reactants up to the transition state. And specifically this would be for the forward reaction. So if I call this say K forward, K reverse. Then also, if you're going in the reverse direction, you have a much larger activation barrier to go from products to reactants, which is why that this reaction is endergonic or exergonic in general, why it's spontaneous, because it's harder for the products to go back to reactants than it is for the reactants to go to products. So this reaction happens at a much quicker rate than this reverse reaction does. Thus, you build up products and you have this net lowering of your Gibbs energy. So that would be the delta E of activation for the reverse reaction. And then also of interest to us is this difference here, which is actually the delta E of reaction. So the products minus reactants, the products are lower in energy, so we had a lowering of energy during this reaction, so it is spontaneous. If this was the Gibbs energy, it would be spontaneous, and we would say that that's an exergonic reaction. Okay, so marking down some of those things that I said during that whole rant there, we have delta RE is the energy change of reaction, the same delta E of reaction or delta G of reaction, delta H of reaction, what have you, that we discussed during equilibrium and all of those other playlists. You have delta E of activation, which, as I said, comes from the Arrhenius equation and tells us about how the reaction rate will change with temperature. Okay, and our transition state is something that doesn't exist for any kind of finite amount of time. It's just something that is a kind of fleeting moment as the molecules go from one side to the other. And that double dagger is usually just a symbol indicates activation or transition states. All right, so that's a single reaction over here, or something that we might call an elementary reaction. So I might call this an elementary reaction. Something like we've got over here, I might call that a multi-step reaction. And it is composed of multiple elementary reactions. R to P in this case is an elementary reaction. What we've got over here is you have your reactants, then you have your first transition state, which I'm going to call transition state 1. Then you actually have a stable, kinetically stable molecule in the middle here called an intermediate. It exists for a finite period of time, so more than a few femtoseconds. Maybe it exists for picoseconds, maybe it exists for nanoseconds, microseconds, milliseconds, maybe it exists for minutes at a time. It's just some intermediate between the reactants and the products. And I'm going to call this intermediate 1 because we have multiple intermediates in this 3-step reaction. Then that goes up to over an activation barrier to transition state 2. It goes down in energy to intermediate 2. Intermediate 2 is stable. It exists for some finite amount of time. And then you go to transition state 3, which you pass your final activation barrier going all the way down to your products, P. So the total kind of net reaction here would be reactants going to intermediate 1, which goes to intermediate 2, which goes to products. All right, and then you have all these different rates for this. You have K1, K2, K3, and all of their reverse rates going from I1 to R is K minus 1. I2 to I1 would be K minus 2. From P to I2 would be K minus 3. And this has all of its individual reaction activation energies, all of its individual reaction barriers along the way. So this would be delta E. I'll call this delta E1 of activation. Call that delta E2 of activation. I'll call that delta E3 of activation. Going from this reactant to this intermediate, let's see, it's getting kind of crowded. Can I use another color here? I'll use purple. Okay, so that's our delta E of reaction 1, going from the reactant to the intermediate. Delta E of reaction 2, going from the intermediate to intermediate 2. Intermediate 1 to intermediate 2, delta R. And then finally, going from the intermediate 2 to the product, delta R E3. And our total net delta E of reaction, we know is just the sum of those three, delta RE1, delta RE2, plus delta RE3. Okay, and you could also look at these reactions going in reverse. Going from I1 to R, you have to pass this activation barrier, delta E minus 1 of activation. Going from intermediate 2 to intermediate 1, the reverse reaction 2, you'd have to pass, I'm going to put this on the outside there, delta E of activation minus 2, giving us rate constant minus 2. And also, you have the reverse here, going from products to transition state 3, if you went to reverse reaction 3 from P to I2, delta E of activation minus 3. Okay, so that gets kind of messy in there, but you see that this multi-step reaction is composed of 3 elementary reactions, R to I1, I1 to I2, I2 to P. And those 3 elementary reactions each have their own activation barriers. They each have their own energies of reaction, and those energies of reaction sum up to the total energy of reaction. But we're going to start studying reaction mechanisms and see that usually if one of these barriers is much, much bigger than the other, then that barrier can be what leads to the rate limiting step and is the big factor in what the rate of the overall interaction is, which would usually be determined by what the highest energy species is in the entire reaction. So in this particular case, we'll go on to see that K1 here is probably going to be the factor that controls how fast the forward reaction occurs, and it's going to dominate how long it takes for us to go from reactants all the way through our 3 steps to products.